So it says find the points that are the relative extrema of the function on the interval 0, 2. So looking at 1/2 x, I know that that's continuous and differentiable. Looking at sine x, I know that that's continuous and differentiable. So then I know that I can apply the first derivative test. So what I'm going to do is find f prime of x. And then derivative of sine is cosine. So I get 1/2 minus the cosine x. And then first derivative test says find where it is equal to 0 or does not exist. So you solve cosine x equal to 0 with the 1/2. So then you get the cosine of x equals 1/2. So now you need to know, okay, what are the trig values at which the cosine of x equals 1/2? What? Pi thirds.
So do we only have to have that one, or do we have to have the other one too?
It's on the interval 0 to 2 pi, so you would also need the other one. So pi thirds is the first one. So yeah, so it's down. 7 pi thirds is pi thirds. Yes. So this only said to find the points. It didn't say to identify which is which. But we know that we need to confirm their extrema. So now you have your two choices. You can do your sine chart, or you can do the second derivative and looking at if it's positive or negative. So what's our preferences? I mean, actually, technically I lied. It says first derivative test, so that would mean you have to do your sine chart.
To be honest, I didn't start doing either. I started doing the campaign test thing.
Oh, the candidates test.
Yeah.
That would give you the values, but you don't need the endpoints because it's an open interval, so not EVT. All right, so what's something less than pi thirds, but greater? It can't be 0 because 0 is not included in our interval. Yes. Yes. I was going to say you could also do pi fourths. Like any of those are fine. So pi 6, so that would give you 1/2 times pi 6, which is pi 12ths. And then what is the sine of pi 6? 1/2. So pi 12ths is going to be smaller than 1/2. So that is going to be negative. And then plug in pi halves, because that's very easily between this. You could also plug in pi. So pi halves is approximately, so I'm plugging in pi because I decided I know that is easier. Because up here that would create pi halves, which I know is about 1.57. And then minus the sine of pi, which I love doing because sine of pi is, yeah. So I changed my mind to pi after I said pi halves just because that was easier. So 1.57 minus 0 is going to be, yep. And then something between 5 pi thirds and 2 pi. There's not a whole lot of like wiggle room in there. So yeah, you got to go with 11 pi 12ths. And again, that's going to give you 11 pi over 24, which is really, 11 times 3 is 33. 33 over 24 is like 1.2-ish. Like it's not going to be anything. Minus the sine of 11 pi over 12. So sine of, not 12, sorry, 11 pi over 6. So the sine of 11 pi over 6 inside quadrant 4 is going to be negative. So you have a minus, which makes that a positive. positive. So a positive plus a positive is going to create a positive. So pi thirds is our extrema. Good? Okay, B, find the points of the relative extrema of the function, blah, blah, blah. So right away in my head, I'm thinking about the fact that that's to the 2/3 power, which means that I'm going to have a cusp. The cusp is going to occur somewhere on my graph, and we'll learn that it's going to occur when the derivative does not exist. So I actually being able to find my derivative and look at this, I will find those two little cusp points at the derivative dNe's because I know they're not differentiable. So f prime of x equals 2/3 x squared minus 4 to the negative 1/3 times 2x. 2x times 2 is 4x. The 3 and x squared minus 4 to the 1/3 drop to the denominator. So then f prime of x equals 0 when 0 equals 4x, so when x equals 0. And f double prime of x does not exist when 3x squared minus 4 to the 1/3 equals 0. So anything divided by 0 is 0. So when x squared minus 4 to the 1/3 equals 0, how do you get rid of something to the 1/3? You cube it. But 0 cubed is still 0. So you get x squared equals 4. So you get x equals plus or minus 2. So again, those are my 3 critical points. So I'll test point -1, +1, 3, and -3. So -3 on top is going to give me a negative. -3 squared is 9. 9 minus 4 is 5. The cube root of 5 times 3 is positive. So negative divided by a positive gives me a negative. A -1 on top over, or a negative number on top, over -1 squared, which is 1. 1 minus 4 is -3. So the cube root of a negative number is negative. So you get a negative on top and a negative on bottom. So that's positive. Here, plugging in 1, you're going to get a positive divided by a negative again. So now we get a negative. And then 3 is going to give you a positive over a positive. So you have a positive. So the graph goes down, up, down, up. So at -2 and 2, those are my cusps. So this is like my little wingbird. That's kind of what the graph is going to look like. The 0 is going to be smooth because it's differentiable. The -2's and 2's are cuspy. Does that make sense? So then -2 and 2 are my mins, and 0 is my max. And again, these are relative because they're not, they might actually be absolute mins because of the nature of the graph, but it's a relative max because the graph is continuing infinitely. So we would end up seeing that the -2 and 2 are absolutes, but it's only asking for relatives. Moving on, are we okay with first derivative test then? So the second derivative test and continuity come into play. So that's when we look at our second derivative. We want to look for positive and negative. That gives me my concave up and concave down. And then within that, we have our second derivative test, which gives me my extrema. So example number 1 says determine the open intervals on which the graph is concave up or concave down. So you're going to find your first derivative, but do absolutely nothing with it, because it didn't ask for anything about it. So we're just going to find it and move on. Then I'm going to find my second derivative, set it equal to 0. So I get x equals 0 and x equals 2. These are my critical points. They are my potential PPOIs. So then again, I'm going to do my number line test, and I'm going to plug in -1, 1, and 3. When I plugged into my factored form. That's why I have like the double pluses or minuses, because I was looking at that and then I was saying, okay, positive. Actually, I plugged -1 in here because I knew it would be squared and positive, but the other two I plugged into factored form, just trying to make my math easier. So it goes positive, negative, positive. So up, down, up, which means 0 and 2 are points of infection. So it says to justify your answer, so we're going to work today on what that means. So we would say that f of x is concave up from -infinity to 0 and 2 to infinity, and then your reasoning is because f double prime of x is greater than 0, or you could write is positive. So that is your justification. So if it asks you to justify your answer, you have to tell me why, kind of based off what you got from the sign chart. The sign chart doesn't act as a justification, it acts as a knowledge enhancer. Your justification is your sentence. So f of x is concave down because the second derivative is 0, is less than 0. And then f of x has a point of inflection at x equals 0 and x equals 2 because f double prime of x changes sign at these points. Okay, let's do the second example because everybody hates fractions. So f prime of x equals ho d high minus high d ho all over ho ho. Okay, so I'm not even really going to clean that up a whole lot. I'm going to cancel out my 0, take my second derivative. First thing I notice is everybody has an x squared plus 3. So I'm going to cancel the 1 away from this side, take 1 away from here, take 1 away from the bottom. I also notice both terms have a negative 12, so I'm going to factor that out because it'll make my numbers smaller. So negative 12 times 3 minus 3x squared all over x squared plus 3 cubed. Set the top equal to 0. Set the bottom equal to 0. We know anything cubed is going to be cube rooted. We know the cube root of 0 is 0. So I kind of null and void that step. And you end up getting x squared equals negative 3, which is imaginary. So there are no points in which this derivative does not exist. So goodbye denominator. And then in the numerator, you get 3 equals 3x squared. So dividing by 3, you get 1. So that means x equals plus or minus 1 are my critical points. So then on my number line, I'm going to look at 0, 2, and negative 2. So I have a negative out in front. Negative 2 in here becomes squared, so it's positive, but then you have a 3 minus 3x squared, so anything times 3 is going to be greater than 3, so that's negative. And then the bottom, this is squared, so that's always going to be positive. A squared plus a positive is always going to be a positive, so your bottom is always a positive for all of the problems, so you can almost ignore it. So you have a positive over a positive, which is a positive. For 0, that goes away. So you get a negative times a positive, which is a negative. And again, that denominator is positive. So you get a negative. And for 2, you're going to get the exact same answer as negative 2 because of everything being squared. So we know that it's a positive. So then concave up, negative infinity, negative 1, 1 to infinity. Concave down, negative 1 to 1. POIs at x equals plus or minus 1. And can you do your justifications based on the statement from above, knowing you'd write because f double prime of x is less than 0, because f double prime of x is greater than 0, etc. Table time. I like table problems. So I like to read through this and mark down, circle, or highlight anything I think is important. Given the following function values for f, f prime, and x, knowing that f prime only has 2 zeros on the interval negative 3 to 10. F prime has 2 zeros. So if f prime has 2 zeros, those zeros are our critical points. That means that f prime has 2 critical points. F double prime has only 2 zeros on the interval negative 3 to 10. Answer each of the following. Identify all x values where f has a relative min. So in order for f to have a relative min, the derivative needs to equal 0 or be dne. So the derivative is 0 at negative 1. The derivative is 0 at 3. And the derivative is undefined at 7. So I have negative 1, 3, and 7 as my critical points. Then what I'm going to do is just take the f primes around those numbers and mark their signs. So to the left of -1 at -3, the derivative is 1. 1 is, yeah. So that means that f of x is increasing. Next, we have a negative. And then we have a positive and a positive. So that means my graph goes increase, decrease, increase, increase. So it asks me to identify the relative mins. So where is my min? At x equals? Perfect. So you would say f has a rel min at 3, -4, because we know the y value. And you don't know, well, it says, I guess it says identify all x values. And then I would say f has a relative min at 3, -4, because f prime of x equals 0 at x equals 3, and f prime of x changes from negative to positive. Or instead of saying f prime of x changes from negative to positive, you could say, you know, something about because f prime of x changes from negative to positive, f of x goes from decreasing to increasing. But this is your justification. You can't say what f is doing because you have no idea. We do know this leads to that, though. Does that make sense? Okay, identify all of x values where you have a max. Well, the work is already done right here. So all you have to do is put that into a sentence. Now, the problem is, what does it say? So we know it's at -1. So you could at least earn a point. So you could say f has a rel max at x equals -1. And if you didn't pay attention and read the directions, then you would probably give that justification. But if you read the directions and paid attention, then you would say f has a relative max at x equals -1 because f double prime of x equals -1. Whoops, sorry, I thought you could see me pointing. Which is less than 0. And by the second derivative test is therefore a rel max. So you're just proving that you know the second derivative test talks about the second derivative sine. Okay, points of inflection. So potential points of inflection are at the zeros or DNEs of the second derivative. And then they come when you have a sign change. So over here, these are negative, so it's concave down, positive, concave up, and then positive, concave up. So point of inflection can only occur when you have a sign change around the 0. Therefore, my only point of inflection is at 1. So 1, I know, it's tricky. So x equals 1 on f is a point of inflection because f double prime of x equals 0. And f double prime of x is less than 0 for x values less than 1. And f double prime of x is greater than 0 for x values greater than 1. Another way of talking about f double prime of x changes from negative to positive. You could talk about it this way as well. You could also go back and revert to the sentence from up here. I'm just giving you different justification writing sentences. And then, I mean, come on. They're not going to give you every problem about extrema. They're going to throw back in there a tangent line. So it says, what's the equation of tangent line to the curve? And it's been so long since we did one of these. So remember, what do you need to write a tangent line? You need the point, and then you need the slope at that point. So the point is going to be when x is 5. So then you go up here, you go to your table, and you say, oh, when x is 5, y is, and then you go and you say, okay, I also need the derivative at 5. So to write the equation of my tangent line, I need the point and the slope. So y minus 3 equals 2, x minus 5. Wham, bam, thank you, ma'am.
I like that one.
Good. All right. So here it says you are given a graph of f prime. Sketch me f. If f prime is a constant, what does that mean the function before it was?
Linear.
And what does that mean the slope was? So that means that a possible graph of x is 2x plus some y-intercept. So you don't know your y-intercept. So as long as you draw a graph with a slope of 2, it doesn't matter if you go through the origin. It doesn't matter if you go through -2. All that matters is that you go and follow the slope rule. Make sense? Okay, next way, if you are given a linear, that means that the graph before it was, yep. So this is y equals x. So that means this is like y equals x squared, again, plus some number or y-intercept. If you want to be normal and just go through the origin, then you have 0, 0, 1, 1, and then remember 2, 4. Because the y's are all your perfect squares. Now, this is a derivative graph of negative x squared. You kind of know that, right? So this is y equals negative x squared. We can figure that out because we can see it. So we know that the function that comes before it is going to be something like cubed, but again, all that stuff happening after. So if you do your analysis, if the derivative is increasing and negative, then your original graph has to be what? Concave up and decreasing.